Why existence? Why the quantum? Can we ever expect to understand existence? Clues we have and work to do to make headway on that issue. Surely someday we can believe we will grasp the central idea of it all as so simple, so beautiful, so compelling that we will all say to each other, "Oh, how could it have been otherwise? How could we all have been so blind so long?" This excerpt conveys the ambition and optimism of American physicist John Wheeler. He sets a high bar. So that we don't get discouraged, let's remember that the origin of species was a mystery for all human history until Darwin came along. Quantum mechanics has been with us only for a century or so. We will know that Wheeler's vision has been realized when we hear words like this. My reflection when I first made myself master of the central idea of the origin was, how extremely stupid not to have thought of that. My name is Zach Walton, and the title of this presentation is Quantum Mechanics as Naturalized Time, condensed to the term quantism. Here I propose answers to Wheeler's questions, why existence and why the quantum? My approach is to combine two threads. First, a suggestion from William Wooters that quantum mechanics may be derivable from a careful examination of what we mean by time. Second, a proof by Lucci Hardy that quantum theory can be derived from surprisingly spare assumptions, the crucial one being that the number of real parameters needed to characterize an n-state system is n squared. The summary of my argument is as follows. Wooters makes a convincing case that we need a mechanism for time passage, but he stops short of proposing one. I propose a specific mechanism called correlated selection. Correlated selection implies that observers will use a particular number of real parameters to describe a system. This number also happens to be the number of real parameters used in quantum mechanics. Hardy proved that if we only know the number of real parameters used to describe a system, we can derive the structure of quantum mechanics. Said another way, my completion of Wooters' proposal for naturalized time leads to certain constraints on the physics that we may find. Hardy showed that there is one and only one solution to these constraints. Thus, we arrive at the following answers to Wheeler's questions. Why existence? A solution exists. And why the quantum? The solution is unique. This talk relies on ideas in math extending to the college level and ideas in physics and philosophy extending to the graduate level. The arguments are not particularly long or technical, so I hope that a broad audience may find some value in what I have to say. References to all the sources I mentioned are at the site linked in the description. First, I present a conjecture that I will later connect to the idea of existence in the quantum. Imagine a circle of radius 1/2 centered on the origin in the xy plane with points P1 and P2 on the perimeter. What is the distance between P1 and P2? We can consider different distance functions expressed as a function of the angle theta. For example, the Euclidean distance is in red. I use the vector notation such that P1 vector corresponds to the vector that starts at the origin and ends at point P1. There is another distance function, d sub c, which is depicted in blue. I have used the definition of the dot product and a trig identity for this step. I chose the notation d sub c because we will see that this particular distance function is related to the notion of center of mass. I note parenthetically that 1 minus d sub c is the quantum formula relating angle in Hilbert space and measured probabilities. This will be relevant later. Next, I consider a kind of mileage chart, where the distance between any 2 points is found on a particular square. Note that for all distance functions, the diagonal of this chart is 0, and that the chart is symmetric about the diagonal. Furthermore, regardless of the distance function used, the chart is overconstrained. Assuming P1 and P2 are not identical or antipodal, if we know the first 2 rows, we can calculate the rest. This is because the points have state, which can be expressed, for example, as an angle between 0 and 2 pi relative to the positive y-axis. Next, I consider a kind of statistical object that is composed of sets of points with an associated probability distribution, such that these probabilities sum to 1. Those familiar with quantum information theory will recognize that this construction relates to the concepts of pure and mixed states. We use the notation convention that lowercase letters represent points on the circle, while uppercase letters represent these statistical objects. We can visualize these statistical objects graphically as a set of points on the circle with size proportional to the probability, and we can construct a center of mass vector which starts at the origin and ends at the center of mass of the points. The reason for our interest in the center of mass will be made clear later. We generalize the notion of distance, as in the bottom left of this slide. Now we consider a mileage chart with these statistical objects, and we arrive at the question relevant to our conjecture. Is this chart overconstrained? Said another way, for a given distance function, do these objects have state? Implicit in the notion of state is that the number of free parameters in the state should be finite, while the number of parameters in the initial definition of the objects can obviously be infinite. I propose conjecture C1 as follows. Mixtures have state if and only if the distance function is d sub c. I label the conjecture C1 to indicate that the underlying state space manifold, i.e. the circle, is a one-dimensional object. We will generalize this conjecture by extending to 2 dimensions later in the presentation. The right to left direction of this conjecture is demonstrated here. Because the dot product is linear, we can rewrite the distance between these statistical objects as a relation which depends only on the center of mass vectors. Thus, it is straightforward to demonstrate that if the distance function is d sub c, mixtures have state. Proving the other direction of the equivalence is surely more difficult. I am by no means familiar with all the fields of math that may be relevant to this question. If anyone has any ideas or corrections or clarifications, I would greatly appreciate them reaching out to me. My email address is in the description. Later, I will make an argument that Hardy's 2001 paper provides something very close to C1. Science is stories, and Chris Fuchs and Scott Aronson are very good at storytelling. Following their lead, I will tell the story of quantism by reviewing my path to the idea. As an aside, if a young person were to wonder what it is like to be a certain kind of scientist, the books, talks, and blogs of Chris and Scott are a great place to start. My uncle, Peter Walton, told me about Bell's theorem. Here is Pete as a standout fullback for Dartmouth College. Pete is a remarkable man in many ways, and he plays 2 important roles in this story. He was introducing me to the game Go, and in that austere setting we started talking philosophy. I was puzzling about the compatibility of determinism and the first-person experience when he presented Bell's theorem, as evidence that modern physics was leaning away from a clockwork mechanistic view of the universe. The surprise of Bell's theorem motivates much of the work described in this presentation, so I will revisit a version of the story Pete told me, with modifications inspired by a masterful telling of Bell by David Mermin. Imagine 2 boxes, each with a button on top, and a display that reads 1 or 0. The way these boxes work is that when the buttons are pressed, the same value, either 1 or 0, appears on each display. This effect works even if the time difference between button presses is so short that there is no time for light to travel between them. This effect could be explained if each box had matching lists of 1s and 0s, and the button push was simply sampling from the lists. The amazing fact is that we have very good reasons to believe that these lists do not exist. Said another way, there is no measurement, even in principle, which could reveal whether a 1 or a 0 would appear on the display before you press the button. Given these facts, there is no way these boxes could operate without them being connected by superluminal signals. At the same time, it is impossible for the users of the boxes to send information using the boxes. After all, they would need a choice of buttons to press to send a signal. This is the core of Bell's theorem, and the best presentation I have found of the details is in the work of David Mermin. This effect is in some sense a limited communication channel, like an engine with a restrictor limiting top speed. Why should nature work like this? Why should there be resources like non-local influences that are restricted in such a way that relativity is not explicitly contradicted? The surprising dissonance between quantum mechanics and relativity is a powerful motivator for understanding where quantum mechanics comes from. It is commonly noted that Bell's theorem is not strictly about quantum mechanics. It merely provides an argument that certain statistical results cannot be observed without a signal passing from one site to the other. Given that we observe these statistics in the lab, we might wonder, can we harness this non-local influence to send signals? Just because quantum mechanics does not afford this ability, who is to say quantum mechanics is the final word? Indeed, proposals have been put forward to harness this effect to send superluminal signals, just as many proposals have been put forward to generate free energy from perpetual motion. Of course, the signaling proposals violate quantum mechanics, just as the free energy proposals violate the second law of thermodynamics. Pete's first role in the story was introducing me to the great surprise of quantum non-locality. His second role was telling my father about Doug Hofstadter's book, Gödel Escher Bach. At some point in my teens, I pulled this book down from my father's bookshelf. It is hard to express how important this book is to me. It furnished the entire intellectual landscape of my life. Doug is a singular individual. He is a virtuoso in a genre he invented. I will have more to say about Doug and his book later, but for now, I mention three themes of the book that play prominent roles in this story: pattern on multiple levels, analogy, and recursion. The next milestones in the quantism story happened while I was in college. The summer after my freshman year, I was lucky enough to connect with Doug Hofstadter and to spend time with his research group at Indiana University. We met weekly at the Runcible Spoon in Bloomington. On one occasion, I casually mentioned that the self is an illusion, expecting Doug to agree. His reply stopped me in my tracks. For whom? He was not disagreeing, but pointing out that the term illusion sells this concept short. We will see that steering clear of illusionism in the context of time is the crucial step for our argument connecting time and quantum mechanics. During my junior year of college, I read the superb book Darwin's Dangerous Idea by Tufts philosopher Daniel Dennett. Nestled in a footnote is the following passage. I sometimes wonder if there is any important advance in thinking in the second half of this century that von Neumann is not the father of. The computer, the model of self-replication, game theory, and if that weren't enough, von Neumann also made major contributions to quantum physics. For what it is worth, however, I suspect that his formulation of the measurement problem in quantum mechanics is his one bad idea, a sleight-of-hand endorsement of a fundamentally Cartesian model of conscious observation that has bedeviled quantum mechanics ever since. Dennett is identifying a connection between von Neumann's conception of the collapse of the wave function and Descartes' dualistic model of consciousness. Several years later, I was able to extend this parallelism in a way that clarified several topics in my mind, as we will see shortly. My senior year of college, I had the good fortune of taking a course on philosophy of physics from Simon Saunders, an Oxford philosopher who was, at the time, a visiting professor at Harvard. Saunders is a world-class philosopher and a superb teacher, and I was inspired to dig into his work concerning the philosophy of time and quantum mechanics. In a paper titled Time, Quantum Mechanics, and Probability, Saunders makes a conditional argument that will provide an important reference for my approach. Like Dennett, he was identifying a parallelism between topics, in particular, the problem of time and the measurement problem. In both cases, there is a multiplicity that physics apparently does not resolve. In the case of time, the four-dimensional timeless block universe seems to lack a correlate for our experience of a sequence of nows. In the case of quantum mechanics, the math of Hilbert space provides us with probabilities of specific outcomes of a measurement but offers no correlate for the cause or even the reality of specific outcomes that we experience. Saunders' point is that if the multiplicity offered by quantum mechanics is unacceptable, then so too should be the multiplicity of the block universe. If one theory is deficient, so is the other. That is, they are partners in guilt. Since the vast majority of physicists have reconciled themselves to the block universe, he argues that they should be equally accepting of the many worlds interpretation of quantum mechanics. He makes this argument not to dissuade the reader of the block universe, but rather to bolster acceptance of many worlds. In his telling, they are both innocent. For the purposes of our story, this parallelism does more work than just analogy. We will claim that the problem of time really is a problem, and it is in fact solved by quantum mechanics. Adapting Saunders' language, we may call our argument an unexpected exoneration. Instead of taking the prevailing view that time is an illusion, we will propose a specific mechanism for time and show that this leads to the mathematical structure of quantum mechanics. This presentation is about quantum foundations, but there is a close link between work on foundations and work on applications, as argued in this excellent paper by Hardy and Speckens. A good way to understand what is novel about quantum mechanics is to try to figure out what new things it allows you to do. My PhD work embodied this connection, and I will briefly summarize those years here. I went to Boston University to work with Tom Toffoli, an extraordinary individual who has made seminal contributions at the intersection of physics and computer science. If any of my work proves useful to others, Tom is the reason. The magnitude of my debt to him exceeds the scope of this presentation, but I can still this discussion to the observation that his approach to science is characterized by deep insight, honesty, and joy. I was also very lucky to have as teachers and collaborators the following individuals: a distinguished information theorist named Lev Levitin, a group of experts on quantum optics who were responsible for funding most of my work, Alexander Sergeyenko, Baha Salah, and Malvin Teich, and a fellow PhD student named Ayman Aburadi, a genius in mathematical physics who displayed good cheer at all times. Another crucial connection was my chance meeting with two remarkable physicists, Chris Adami and Nicholas Cerf, who were working at Caltech at the time. Chris and Nick were extremely generous with their time, and their work helped me think more clearly about quantum foundations and applications. I will summarize my work on applications first. Along the way, my debt to Hofstadter is demonstrated by the use of the concepts of analogy and pattern on multiple levels. The connection between quantum non-locality and practical applications is surprising, but not hard to understand. Think of the construct I mentioned earlier, two boxes which work such that when the buttons are pressed, a 1 or 0 appears on each box, such that the values match. Previously, I had stressed the surprising fact that the time interval between button presses can be shorter than the time light would take to travel from one to the other. Furthermore, the particular value on any run of this experiment is fundamentally random. Another way of saying this is that no one besides the people holding the boxes knows the result. These boxes are a mechanism for generating random shared secrets. It turns out that random shared secrets can be used to enable secure communication over public channels using a technique called the one-time pad. My work on applications had to do with using quantum mechanics to implement secure communications, a field known as quantum cryptography. The following timeline explains how I arrived at the primary result of my PhD. By putting myself on this timeline, I don't mean to suggest my contributions are as significant as the other events. The construction is merely to show the heritage of my work. The timeline begins with the EPR paper, in which Einstein and coworkers identified how quantum entanglement leads to something we now call quantum non-locality. This is a space-time diagram of so-called EPR pairs. Bell's work solidified our understanding of how this type of non-locality could not be produced with classical physics. In 1984, Charles Bennett and Gilles Brassard invented quantum cryptography with a scheme in which information is encoded in the state of one photon which is sent from one participant to the other. The space-time depiction of this scheme, in which a signal is sent from one participant to the other, is represented by a diagonal line in space-time. I have labeled the participants in this communication scheme A and B in reference to the traditional names used in the field, Alice and Bob. In 1992, Arthur Eckert showed that entangled pairs can also be used to implement quantum cryptography. Ever since Bell's work, there was a race to demonstrate quantum non-locality in the lab. It was Eckert's genius to connect these proofs of fundamental physics with the practical task of quantum cryptography. Here I mention the crucial principle that drove my work. Even prior to Eckert's work, it was known that there is a duality between two photon experiments in which a single source produces a pair of photons which are measured by two detectors, and one photon experiments in which one of the detectors is replaced by a photon source and the two-photon source behaves like a reflector. This duality is known as the advanced wave interpretation of quantum non-locality. In space-time diagrams, the advanced wave interpretation helps you understand the experiment described by Eckert in terms of an experiment described by BB84. That is, the trajectory of one of the photons is reflected about the time axis. One could say that the way the non-local correlations are produced is by a wrinkle in time. Of course, in practice, it is still impossible to send information back in time by doing these experiments. This construction is merely an aid to an intuition. It is true, however, that had someone been thinking about this connection between one photon and two photon experiments, they would have been able to see that BB84 implies a two-photon EPR-based version immediately. That is, Eckert's work can be seen as applying the inverse of the advanced wave interpretation to BB84. During my PhD, I was studying practical implementations of quantum cryptography, and I came across one that had a particular space-time signature. A research group led by Nicolas Gisin had noticed that if instead of a one-way trip, you send a photon on a round trip, the entire setup can be made immune to certain types of noise that may be present on the channel between Alice and Bob. One way to see why this is important is that in typical implementations, the precision of the results rely on optical setups that must maintain submicron stability over large distances and times. It occurred to me that Eckert's inverse advanced wave interpretation trick could be used again, such that by flipping one leg of the photon's journey around the time axis, a round trip for one photon became a one-way trip for two. Further impetus for thinking about this wrinkle in time came from a paper of Adami and Cerf, in which they point out that entangled pairs behave in certain ways like particle-antiparticle pairs in particle physics, such that the antiparticle may be viewed as a regular particle moving backwards in time. One practical consequence of converting a round-trip scheme into a one-way version is that if the noise on the channel is changing quickly, say on the order of the time required for a one-way trip, the one-way method will remain immune to the noise while the round-trip method won't. This was the first time in my life I had arrived at a result that was new and important, and it was a direct result of using the techniques of analogy and thinking on multiple levels that I had learned as a teenager reading Gödel-Escher-Bach. Ever present with insight and support, Ayman Abarati was able to show me that this result fit into the literature for noise-tolerant quantum computation. Essentially, the main practical result of my PhD was that practical error-correcting codes exist for quantum cryptography. It was particularly gratifying that the final paper we wrote on this topic was accepted without edits in Physical Review, which was the journal Einstein chose to highlight quantum non-locality years before. A PDF of my PhD thesis is available through the link below. In parallel to the work I was doing on applications, Tom Toffoli and I were thinking about Wheeler's challenge of finding where quantum mechanics comes from. The upper side of this timeline shows some significant events along the way. The first event on the Foundation's timeline is a paper by Wheeler's student William Wooters. It is a remarkable result. For me, it represented a persuasive clue that the structure of quantum mechanics is not arbitrary, and that the program of deriving quantum mechanics from simpler principles is likely to succeed. Because of the importance of this result, I will summarize the math graphically here by marking up a diagram from Wooter's paper. Imagine you are sending a signal to a friend, and the signal amounts to one letter from a 10-letter alphabet. Instead of writing the letter on a slip of paper and putting it in the mail, imagine you must instead send one of 10 unfair coins, such that each coin has a distinct probability of landing heads. Your friend will be given a fixed number of flips of the coin, say 20 flips, in order to guess which of the 10 letters you wanted to send. How should you map the 10 letters to the probability interval 0 to 1 so that the probability of your friend guessing your message incorrectly is minimized? One might be tempted to distribute the letters linearly along the interval, but by inspecting the expected fluctuations, it is easy to see that this would not be optimal. Imagine that the probability of heads is 0.4. If we flip this coin 20 times, the most likely number of heads is 8, but it is of course possible to get any number between 0 and 20 heads, with probabilities given by the binomial distribution. The binomial distributions for coins with probabilities of heads close to the endpoints of the interval are narrower than those at the middle. Thus, to minimize overlap, we should crowd the choices near the endpoints. Wooters shows in his paper that the optimal mapping from state space to probability space approaches this sinusoid as the number of letters in the alphabet goes to infinity. This is the same sinusoid we saw earlier in the presentation related to the center of mass distance function and the quantum formula which maps distance in Hilbert space to probability space. Why should the mathematical structure of quantum mechanics have the same form as a solution to a communication channel problem? We regard this as a clue that quantum mechanics can be derived from simpler, ideally self-evident principles. The next event on our Foundations timeline is Wooter's 1996 paper titled, "Is Time Asymmetry Logically Prior to Quantum Mechanics?" Wooter's 1981 paper was a clue. His 1996 paper was a plan. Wooter's argument is as follows. Instead of the usual plan of proposing some mathematical description of the world, and then later on figuring out the implications of that math for actual measurements made by observers, Wooter starts with a specific characteristic of all measurements, i.e., the distinction between before and after, and suggests exploring the impact of that non-negotiable characteristic on the physics that we see. He goes on to speculate about the nature of this before and after distinction, noting that it is likely that this distinction won't be an objective fact about the world, but something like the consequence of choosing a point of view. In his own words, without justifying it, let me simply record here my own view that it will probably not be possible to maintain a rigorous separation between objective and subjective, but that this limitation need not keep our physical theories from being rigorous. This statement has echoed in my head as I thought about the connection between time and quantum mechanics. I can't tell if it led directly to the result I obtained, but looking back, the degree to which it foreshadows the path I took is remarkable. So generous is Wooters in sharing his vision, he explicitly identifies what is missing. But remember that there would be in this theory a deep law, the great underlying probability law, that would allow one to compute probabilities and would give rise to quantum mechanics. At this point, it would be great help to my argument if I could produce the great underlying law. Unfortunately, I cannot. I claim in this presentation that the missing great underlying probability law is correlated selection, a simple mechanism that I will describe shortly. The next event on the timeline is a paper by Lucci and Hardy in 2001 titled Quantum Theory from 5 Reasonable Axioms. In this paper, Hardy performs the astounding feat of deriving quantum mechanics from the barest of assumptions. In particular, he shows that if all we know is that an n-state system requires n squared real parameters, we can derive the mathematics of quantum mechanics. As a comparison, classical probability theory requires only n real parameters to describe an n-state system. A note of clarification, in classical probability, an n-state system is typically characterized by n-1 real parameters. For example, an unfair coin is a two-state system and is completely characterized by the probability of heads. Hardy finds it more convenient in his paper to deal with non-normalized states, such that in addition to the probability of heads, we need a probability that the coin was flipped at all. Thus, instead of the typical description of normalized states needing n-1 real parameters for a classical system and n squared minus 1 for a quantum system, we will occasionally use Hardy's construction in which states are unnormalized, and thus require n real parameters for the classical case and n squared for the quantum case. Before Hardy's 2001 result, we wondered why are quantum amplitudes conveniently represented by complex numbers, while after we wondered why do quantum amplitudes have 2 degrees of freedom instead of 1. The game was then to come up with a good reason for the size of the state space. I spent many hours thinking about this and doing what Tom Toffoli affectionately referred to as numerology, playing with models of system-observer interactions, trying to get to n squared. Then, on a very good day in 2003, I came upon a mechanism that did the job. I gave the mechanism the name correlated selection for reasons that will be clear shortly. What made me so happy with the result was that it leveraged the distinction of before and after that Wouters had outlined. It offered an explanation of where quantum mechanics came from by answering the question, what is time? Around this time, I was also reading Dennett's book, Freedom Evolves, and it occurred to me that this approach to time mirrored the resolution of several other vexing topics, such as what is life and what is free will. It is fitting that Dennett was on my mind, given that it was his earlier mentioned speculation about the parallelism between approaches to consciousness and quantum mechanics that planted the seed for this approach. For both life and free will, there is a false dichotomy between an essentialist position and an eliminative reductionist position, and the correct approach lies between them. For example, when trying to understand the distinction between life and non-life, it is a mistake to say that life is fundamental, the discredited Elan Vital, and also a mistake to say that life does not exist. The proper telling of the story of how the concept of life works is more subtle, but no less real because it is not fundamental. Similarly, it is a mistake to imagine that free will derives from a supernatural intervention beyond the laws of physics, and also a mistake to say that free will is an illusion. These positions represent straw men, which do no work as they knock each other over. Over the next few months, I wrote a manuscript that summarized how I believed correlated selection can resolve questions in philosophy of time and foundations of quantum mechanics. A PDF of the manuscript is available at the site linked in the description. I included in the manuscript a table with every one of the topics that I felt could be profitably cast in this false dichotomy framework. One reason I constructed this table was to organize the positions of various references. The general idea of this table is to leverage what we know about the easier and less controversial topics on the left to help guide us with the more challenging topics on the right. For this presentation, I have added a second layer of analogy at the top. The topics bracketed as analogs are different subjects which have conceptual similarity. I point this out because it is occasionally suggested that consciousness may be related directly to quantum entanglement, or that the second law is directly related to the collapse of the wave function. To me, these attempted connections are in fact the combination of two bad approaches, hoping they will result in a good one. I am, however, making exactly that claim about time passage and quantum mechanics. The central claim of this presentation is that quantum mechanics is the answer to what is time passage. Drawing analogy to evolution, these topics are homologs. Positions on the topics of life and evolution are analogous like wings of bees and birds. That is, they do the same work but have different heritage. I claim that the topics of the passage of time and quantum mechanics are the same topic, which only appear distinct because the connecting structure is opaque. Before continuing, let me make an important aside. In this chart, I implicitly criticize the positions on the top and bottom rows. At the same time, I have great respect and admiration for the individuals expressing these positions. I think it is important to show that brilliant people have divergent views on a topic as a way to demonstrate that the question is a good one and not a path to tautology. This chart covers many topics, and even with the accompanying text, it may not be particularly easy to decipher. Allow me then to explain by example what I am claiming and what is at stake. The Maxwell's demon thought experiment purports to show a scheme for violating the second law, which would in turn provide a free energy machine. The proper explanation of why the scheme fails took nearly 100 years to arrive, via the work of Rolf Landauer, Charles Bennett, and independently by Oliver Penrose. However, there is a school of thought that the Landauer-Penrose-Bennett resolution fails, expressed by David Albert in his book Time and Chance. Albert is unconvinced by the argument that thermodynamic entropy is related to an observer's knowledge of a physical system, preferring to interpret entropy as an observer-independent quantity, like mass. But this leaves Albert in the difficult position of being unable to explain why free energy devices relying on a Maxwell's demon can't be built. A second example more familiar to a general audience is the topic of free will. Sam Harris has argued that free will is an illusion. This represents the other side of the false dichotomy on my chart. The problem that Harris has with his approach is that he struggles to make sense of our common usage of the concepts of blame and credit. Shortly after he published the book titled Free Will, Sam Harris had a discussion with Dan Dennett in which he takes the example of an excellent golfer like Tiger Woods missing a short putt. Harris is vexed about whether the extreme rarity of this event should make us think of Woods as more or less responsible for the miss. My view is that Harris's difficulty understanding our intuition and our words in this setting derives from his insistence that free will is an illusion. I believe Harris's failure to see this false dichotomy is also revealed in his comments about artificial intelligence. In a podcast with Lex Friedman, he betrays an essentialist approach by imagining a situation in which he puzzles over the question of whether an AI system that passes the Turing test is really conscious. The word really crops up in the speech of those who fall into this false dichotomy, and this is an interesting linguistic bridge to the central thrust of our approach to time, which is a critique of the philosophical view of time that is often connected to the concept of realism. Similarly, I believe that Albert's insistence that entropy is fundamental is linked to his inclination to physical collapse theories of quantum measurement like the GRW theory. Roger Penrose wrote a book, The Emperor's New Mind, in which he argued that computers can never be conscious, and also expressed the suspicion that evolution showed a kind of striving that exceeded the mechanism of natural selection. I believe in both cases, he is seduced by the false dichotomy of fundamental or illusion. In summary, I claim that the correct approach to these esoteric appearing issues can have very practical benefits, preventing us from chasing free energy, allowing us to make sense of credit and blame, and, as I shall argue later, clarifying the origins of quantum mechanics. My motivation for writing the 2004 manuscript was to organize my thoughts by putting them on paper. The manuscript is not particularly reader-friendly, as I was just trying to get my hands around the ideas myself. Also, there was a missing part. Correlated selection is a mechanism that joins Wouters and Hardy in a new derivation of quantum mechanics, but the argument relies on a mathematical proof that I have not yet been able to construct. More on that later. During the pandemic, I wrote the best version of the argument I could and posted it to the archive. I didn't expect to get much of a reaction, given that the arguments are subtle and the size of the audience familiar with the context is small. But given that the work is still unfinished, in that it relies on a rather simple-to-state mathematical conjecture, I was motivated to enlist the broader mathematical community, and that is why I made this presentation. This slide represents the heart of this presentation. Here I explain the principle of correlated selection as an answer to the question, what is time? When we ask what is time, our task is very similar to figuring out a magic trick. except the magic trick is one we are doing for ourselves. If we were to ask nature, what is time? She might answer, it's your idea. You tell me. This thought is succinctly expressed by Feynman, who said, the first principle is that you must not fool yourself, and you are the easiest person to fool. What follows is a brief summary of our 2020 paper. Our approach is the same as if we were watching a skilled sleight of hand practitioner. Watch closely and keep your eye on the other hand. To do this, we cash out what we mean by time in the cleanest language we can. When we look closely at our lab notebook, we see phrases like, I before prepared the system in state S, then I after performed measurement M, would result in outcome O. Apparently, the concept of time passage cashes out to the relationship between I before and I after. We have expressed the abstract question, what is time, as the more operational question, how are I before and I after related? Our approach to this question is to look at the classical model of measurement and to use Szilard's trick of including the measurement device in the analysis. Szilard took this brilliant step when analyzing the Maxwell's demon problem and almost broke the problem open a half a century before the definitive analysis of Charles Bennett. In the classical model of measurement, a conditional dynamics establishes a correlation between the observer and the system. Here we imagine two classical bits, one for the system and one for the observer. The conditional dynamics are depicted by this transformation. On the occasions when the system bit is 1, the observer bit is flipped. If we narrow our focus to just those cases where the observer bit starts in the 0 state, we see that this operation copies the value of the system bit to the observer bit. When the system bit is subject to a random process with a certain probability of coming up 1, we can model this process as flipping an unfair coin and taking a picture of the result. The key fact is that this process establishes correlation between the system and the observer. Now, we wish to remove the notion of dynamics, since that is what underlies our common sense notion of time passage. But we also want to capture the notion of a transition from a state in which the system and observer are uncorrelated to one in which they are correlated. If we simply relax the constraint that the observer starts in a known state, a solution is apparent. We imagine flipping 2 unfair coins, one for the system and one for the observer, and post-select in the cases when the results match. This is correlated selection. We are identifying I before with the pre-selection uncorrelated state and I after with the post-selection correlated state. This mechanism establishes correlation without dynamics. These 2 words, without dynamics, are the most important of this presentation. A crucial step for me was realizing that a proper explanation of time passage must be free of the notion of dynamics. Just like when you explain color by describing the way atoms of a material absorb and reflect wavelengths of light, you let go of the notion that the atoms have intrinsic color themselves. Wheeler's frequent use of phrases like law without law has relevance here. We will flesh out this story in the next slide, but I want to take a minute to address some natural objections. One might object, it certainly doesn't feel like adjusting the preparation state is affecting the state of the observer degrees of freedom along with the system degrees of freedom. After all, I prepared the photon detector, and I know its state very well before the experiment begins. In response, I submit that this objection smuggles in dynamics as a primitive. Another way to address this objection is to ask, what would it feel like if correlated selection were the actual mechanism at play? I submit it would feel like the standard story of quantum measurement built on the notion of time as a primitive. A second objection, what about those cases when the coins don't match? Why don't we observe them in the lab? This objection is easier to deal with for those familiar with the many worlds interpretation of quantum mechanics, which tells us that we don't see those results because we aren't in those worlds. The advantage of our approach over many worlds is that we make the identification with the particular subsetting and personal identity explicit. That is, we need a mechanism to define I after that doesn't rely on time as a primitive, and the subsetting of correlated selection does the job. In many worlds, The multiplicity is invoked without a rationale, and is thus harder to understand. This is a cursory summary of correlated selection. The paper provides more of the background and motivation, but there are subtleties that I have still not presented properly, either in the presentation or the paper. The next slide is an attempt to provide greater insight into the idea. Consider a two-state quantum system, i.e. the qubit. This could be the polarization of a photon, or the spin of an electron, or the Wiess path information of a photon in a Mach-Zehnder interferometer. The results we would like to calculate are the probability that a given detector fires, given a specific setting of the preparation and measurement devices. We will tell the story of how to calculate these results with traditional quantum mechanics and then with our new approach. In the traditional story, the preparation device has a button on top which releases a particle in a state determined by the settings on these knobs. When the dimension of the quantum system is n, there will be two n minus 2 real numbers required to specify the pure quantum state. We depict these two n minus 2 real numbers by two n minus 2 knobs. In the case of the qubit, n equals 2, thus there are two knobs. It is convenient to represent pure qubits by a point on the Poincare sphere. This expression relates the vector space notation of the quantum state to the geometrical representation provided by the Poincare sphere. The measurement device also has knobs, and these knobs specify the basis in which we are measuring the prepared state. For the general case, the measurement device will have n minus 1 times n knobs. In the case of the qubit, there are two knobs. In the language of geometry, the preparation step corresponds to choosing a point on the sphere, and the measurement step corresponds to choosing antipodal points on the sphere, one for each detector. The probability that a given detector fires is a function of the distance between the preparation point and the detector point, as measured by the angle between these points. As an example, imagine that the angle between the preparation point and the detector point is theta. The probability of this detector firing is given by a function of theta, and that function is in fact 1 minus the distance function we saw earlier in the presentation, d sub c. This mapping of state space to probability space is an application of the Born rule, which connects the formalism of quantum states with frequencies we measure in the lab. This is the traditional story of quantum measurement, and as a dynamical story, it suffers from ambiguity about when and how the wave function collapses. The many worlds interpretation tells a different story, in which the wave function never collapses. To collapse or not to collapse. Instead of making commentary on this question, we point out that both collapse and non-collapse suffer two weaknesses. They don't explain where the formalism comes from, i.e., why a Hilbert space, and they assume time passage as a primitive. Our story attempts to remedy these weaknesses. In quantum mechanics as naturalized time, quantism, we start by identifying the system degrees of freedom and the observer degrees of freedom. For the two-state system, these will be two regular classical bits. We will assign the system bit to be the Wiess path degree of freedom for the particle just to the left of the detectors, and the observer bit to be which detector fires. There's a cleaner way to connect quantism to actual experiments using the concept of quantum non-demolition measurements, but for the sake of brevity, we will skip that discussion for now. It will help to think of these two classical bits as unfair coins, each with probability of heads ranging between 0 and 1. The state space of two unfair coins can be depicted by a square with one coin's heads probability on the x-axis and the other on the y-axis. Now, returning to our apparatus, the two knobs on the preparation device can be thought of as moving the state on this square. Correlated selection is the mechanism that determines the probability that a given detector fires by mapping the square onto the unit interval. We can think of this as flipping both coins, keeping the cases in which they match, and then measuring the fraction of heads in the subsetted results. We call this function correlated selection, abbreviated CS, and draw the contour lines over the square. Linking this to time passage, the before state is characterized by the two unfair coins before they are flipped. The after state is characterized by the subset of outcomes for which the results match. Now, for the transformation described by correlated selection to be measurable by observers, there must be more to the story. If it was only as I have described, the observers would realize that the two knobs on the preparation device are only controlling one measurable degree of freedom, and they would replace the two knobs with one. Correlated selection is a lossy map, in that it maps a larger dimension space to a smaller dimension space via subsetting. Thus, information must be lost in the process. The only way an observer could see the entire preparation state space would be if there were different ways to perform this subsetting. If, for example, there were a way to perform a controlled permutation of the preparation states, we would have different views of the same preparation state, and these different views may be sufficient to reconstruct the entire preparation state. This is the role that the knobs on the measurement device will play. Let us now consider an analogy to shadows, seen here with Hofstadter's triplets. Shadow casting is lossy. That is, a three-dimensional shape is mapped to a two-dimensional space. To reconstruct the three-dimensional state from the shadow, we need to either rotate the object or use multiple light sources. Returning to the case of correlated selection, we now consider what it would mean to rotate the preparation state space. If we had a distance function on this state space, we could use that to define rotations as maps of the preparation state space onto itself that preserve distance between states. Clearly, there are many ways to define a distance function on the unit square. How could we decide which one to choose? Here, the principle that mixtures have state makes its second appearance in this presentation. In this setting, a mixed state is one in which the preparation knobs are not fixed, but rather their values are drawn from certain probability distributions on each run of the experiment. We introduced the concept of mixtures having state earlier when we were discussing distance functions on the circle. In this case, mixtures having state means that for a given mixed state, the results of this experiment run with a finite number of measurement device settings are sufficient to predict the results of the experiment with any other measurement device setting. Is it possible to find a distance function for which mixtures have state? The answer is yes, and we can see this by connecting correlated selection to quantum mechanics via the Poincare sphere. We depict a specific map of the square onto the sphere as follows. The sphere has a natural distance function, in which the distance between 2 points is simply the angle between rays that start at the center of the sphere and pass through the 2 points. Once we have a map between the unit square and the sphere, we can use this natural distance function on the sphere to infer a distance function on the square. Note that contour lines of the correlated selection function are associated with lines of latitude on the Poincare sphere. We have already described how the Poincare sphere is used to calculate results. Now we describe how results are calculated using correlated selection. The settings of the knobs of the preparation device pick out a point on the unit square. The settings on the measurement device describe a distance-preserving map of the unit square onto itself, and the original point ends up at a new point. Finally, the correlated selection function is applied to the new point to obtain measurable probabilities of specific outcomes. By choosing this specific calibration between the contour lines and the lines of latitude, we achieve an important equivalence. For a given setting of preparation and measurement devices, we could use the method of the Poincare sphere to calculate results, or we could use the mechanism of correlated selection with this map, and we would find the same results. Since we know that mixtures have state in quantum mechanics, we conclude that mixtures have state in our new setting as well. I call this specific mapping Wooter's square, since following Poincare, these geometrical structures linking geometry to probability seem to get named after individuals, and I think this is what Wooter's was reaching for when he referred to a great underlying probability law. We are now at the end of the story connecting time to quantum mechanics. We started with the notion of time passage, correlated selection, and showed that it can be made to produce operational results equivalent to quantum mechanics? Can our model of time passage lead to any other physics? We claim that it can't, and this claim is embodied in conjecture C2. Mixtures have state if and only if the distance function used is that of Wooter's square. This brings us back to Wheeler's questions. Why existence and why the quantum? Why existence? Because Wooter's square satisfies the condition that mixtures have state. Why the quantum? Because Wooter's square is the unique solution for this condition. The confidence I have in C2 derives from the fact that Hardy proves something very similar in his landmark 2001 paper. This paper convinced me of the plausibility of Wooter's hunch that quantum mechanics could be derived from time. I will trace the steps of Hardy's proof now. He begins with a mathematical formalism for measurement and preparation states that makes completely reasonable assumptions. By this he means assumptions we can't do without. Then he considers the function k of n, which is the number of degrees of freedom for an unnormalized mixed state. At this step, he is incorporating the principle that we refer to in our work as mixtures have state. It may not be immediately obvious, but we argue that you could not have a coherent notion of physics without this requirement. He then uses some less reasonable assumptions to arrive at the condition that for quantum mechanics, k of n should be n squared. Next is a brilliant move in which he shows that we may focus our attention to the n equal 2 case without loss of generality. This is a pleasing validation of Feynman's quip that the double slit experiment, which reduces to a qubit in the limit, is the only mystery of quantum mechanics. Finally, Hardy constructs a sophisticated mathematical proof that the state space for n equals 2 must be equivalent to the Poincare sphere. In this way, he shows that k of n equals n squared implies quantum mechanics. The difference between Hardy's proof and conjecture C2 is that Hardy starts with the number of degrees of freedom for mixed states, and C2 involves the number of degrees of freedom for pure states. I'm inclined to believe that Hardy's proof can be adapted to prove C2, and I would be very happy if someone with more mathematical skill than me would tackle this problem. I have gone quickly through the technical details of correlated selection, because, to me, that is not where the drama is. The rate-limiting step for accepting this argument is letting go of the block universe. If you agree that the block universe fails as an explanation for time passage, our results follow naturally. But if you do not see a problem with the block universe, our arguments will cut no ice. An important ally in understanding the deficiency of the block universe is Tim Maudlin, the eminent American philosopher of physics. Contra Saunders, he argues that we must have structure to explain time passage, and the block universe does not provide it. To aid in the intuition for how the block universe fails, we imagine an equivalent failure in the theory of color. There was a time when humans didn't know that color related to the wavelength of light. We could imagine them looking at a rainbow and postulating a mapping from color to the number line, even though they didn't know what those numbers corresponded to. They could even develop mathematical theories about how different colors of light would interact with different kinds of prisms, given this mapping, while being completely ignorant to the other parts of science that link light to our experience, i.e. electromagnetism and biochemistry. This subset of the whole story would be the block theory of color. We claim that this is our current stage with respect to time passage. We have a mapping of moments onto the number line, and then embedded in a higher dimensional space-time. But we have not yet connected this mathematics to our experience of time passage. In fact, we do have all of the science for completing the story, i.e. quantum mechanics, but we have hitherto failed to recognize the need and thus failed to recognize the completion. This is why we chose the imagery of the puzzle piece hovering over an empty spot where it fits. All we need to do is drop it in. Why is this so difficult? Imagine taking a dictionary and putting each word on a graph. For a given word, the words in the definition are connected to that word by green arrows. If we want to know what a word means, we follow the green arrows arriving at that word backwards, and this will give us the set of words which, arranged correctly, will provide the definition. Now we overlay this graph with more connections in yellow as follows. Take the history of one person's stream of consciousness for their entire life, all the words they spoke out, all the words they wrote down, all the words of their inner monologue, and depict each transition from one word to the next with a yellow line. A few observations are clear. First, every word must have green arrows arriving at it. After all, it is not acceptable to look up a word in the dictionary and find a blank entry. Second, some words will have many more yellow lines arriving and leaving than others. Some words will have so many yellow lines that the green lines are crowded out and almost obscured. The word I, for example. We call examples like this dandelions. The reason for this construction is to illustrate something Dennett calls the zombic hunch. This relates to the idea that material mechanisms alone fail to explain consciousness. In this setting, we argue that the extreme imbalance of yellow lines and green lines feeds the intuition that the green lines are not up to the task, and they must be supplemented by an extra ingredient that is not linked to the other words. The more a word looks like a dandelion, the harder it is to resist the zombic hunch. This is the dandelion principle. I believe that the dandelion principle provides us insight into why it is so difficult to give up the block universe. For just as the non-material light of the mind tempts us away from a scientific understanding of consciousness, so the conception of the block universe with its smuggled in light of the now tempts us away from a scientific understanding of time passage. The connection was made clear when we unpacked the notion of time passage and found the terms I before and I after. The word I, with its many, many yellow connections, may be the most dandelion of all. An example of the dandelion principle at work is the case of color qualia. Qualia is the name of the supposed residue that remains after all material explanations have been brought to bear for some part of our experience. Why do proponents of this idea often invoke color, say blue, rather than pitch, say middle C, to argue for the existence of qualia? I claim that the reason relates to the fact that in our graph, the word blue looks more like a dandelion, with a much higher yellow to green ratio than middle C. My debt to Dennett is clear as I make this argument. In fact, the argument relates directly to a picturesque telling of the difference between greedy reductionism and good reductionism in his 1995 book, which contains the footnote that planted the seed for this entire presentation. He uses the concept of skyhooks and cranes in the context of mechanisms of biological evolution. By greedy reductionism, he means the principle that we cannot have cranes, in our case, words with inputs and outputs. By good reductionism, he means the principle that we cannot have skyhooks, in our case, words without inputs. It was only after I finished constructing this slide that it occurred to me that Hofstadter was at work in my mind. As I was thinking about diaries, dictionaries, and dandelions, I realized that this construction is very similar to one Doug describes in this paper, which is reprinted in this collection. I encourage all those interested to read this book and appreciate the way ideas develop as they echo from one carinium to another. What might be the payoff if we succeed in this project of answering the questions, what is time passage, and where does quantum mechanics come from? Even if this success did not lead to new predictions to match novel experiments, there would still be value. The quality of explanations matter, as argued in this paper by David Mermin. Mermin has been a guiding light for me. He is a master of clear thinking and clear communication, even when wading in the murkiest of waters. Fortunately, there is good reason to believe success might, in fact, lead to new science. Consider Wheeler's program, It from Bit. The idea is to start with statistics, bits, and derive physics, its. We claim that his student Wooters accomplished this part of the task, modulo the missing ingredient provided here, correlated selection. But what about space? Wheeler is clear that space must get the same treatment. If we were to succeed in deriving space from statistics, we might then see how relativity is a continuum limit. Furthermore, we may be able to merge our theories of space and time at the statistical level so that we are able to avoid the current impasse in unifying quantum mechanics and relativity. An important clue in this project is that the differential equations of general relativity allow closed time-like curves, as observed by Gödel in 1949. This would allow causal contradictions, and I regard this feature of relativity as disqualifying. I regard this as evidence that general relativity is only valid as an approximation in certain limiting cases. This opens the door to possible experiments that could show a discrepancy between the predictions of relativity and the results of experiments which do not satisfy these limits. If this were true, it would be a repeat of the case of Newton's theory of gravity. He worried that the inherent action at a distance of his law of gravitation made the theory incomplete. And we now understand that he was right to worry, as it was later shown by Einstein that Newton's law of gravity is only valid in certain limiting cases. In summary, possible payoffs from Wheeler's program include unification of quantum mechanics and relativity, better predictions for precision space-time measurements which reveal that relativity is valid only in the continuum limit. For example, perhaps we would see the discrepancy between relativity and measurement if we sent an atomic clock around Jupiter, or if we found a way to interpret the size, not just the presence, of gravity waves. Insight into what is going on inside black holes. The recent controversy about whether black holes contain a singularity or not is evidence that there is work to do here. I speculate that getting the story right at the level of statistics may give insight into the question of why we have three spatial dimensions. I often wonder if this is related to the fact that the Poincare sphere is a three-dimensional object. Finally, there may be other payoffs that come as complete surprises. Before concluding this presentation, I would like to point out one coincidence which may have relevance for the project of connecting relativity with statistics. The equation for time dilation is well known. A clock moving at velocity v with respect to a reference frame will be observed to tick more slowly by the Lorentz factor. Any system that has a predictable evolution in time may be used as a clock. Consider a diffusion clock based on a random walk. A particle starts at the origin, and for each time step it moves left or right with probability 1/2. After time t, the width of the probability distribution for the location of the particle is given by 1/2 root t. Let this behavior in time serve as a clock called a diffusion clock. Now consider the same story, but the random walk has a bias such that the probability of moving to the right, p, is larger than the probability of moving to the left, 1 minus p. It is clear that as p approaches 1, the diffusion clock slows down, since in the case p equals 1, the distribution is simply a delta function. But what is the mathematical relationship describing this slowing according to a clock at rest? The algebra here shows that the relationship between the diffusion clocks is identical to the relationship between the clocks in relativity. Is this a coincidence? Maybe so, but maybe not. One way to gain intuition for this question is to look at Conway's game of life, which is a two-dimensional cellular automata. The rules of Conway's life are that the value of each cell, on or off, is updated for the next time moment according to the values of its immediate neighbors. Here is an animation. This world is deterministic and local. It is known that Conway's life supports self-replicating structures and universal computation. Thus, we could imagine intelligent beings akin to humans inhabiting this world, call them lifers. We could even see them trying to study their own physics. What this calculation shows is that if they happen to use diffusion clocks, they would get relativity for free. For a much more sophisticated investigation in this direction, I recommend these two papers by Tom. Consider just the first sentence of this paper. What I would like to do here is to add a few strands to a line of thought which threads through Lucian, Huygens, Laplace, Darwin, Boltzmann, Gibbs, Feynman, Chaitin, Jaynes, and Landauer. If this doesn't make you want to read on, I can't imagine what would. To honor the influence of Doug Hofstadter on my life, I have established the GEB Scholars Program. More details can be found at gebscholars.org. This presentation is dedicated to these giants. There is a grandeur in the view from their shoulders.